Hi, everyone. Welcome back to the last section in Chapter P, Section P6. We're going to continue talking about rational things, but switch up a little bit about where we talk about them. Last section was all rational expressions, where the entire expression is rational, the entire expression is a fraction. But what we're going to do in this section is where the exponents are fractions. We haven't really looked at that a whole lot so far in this chapter, but we're going to really set the stage here and see the kind of things we can do with that. So for us to get to rational exponents, it's a little bit easier if we talk about radicals first, like square roots, cube roots, and so on. So we're going to start right there with square roots. So when we are squaring something, that's like taking 5 and squaring it to get to 25, right? 5 squared is 25. Now, we would then say that the square root is going from 25 back to 5. So squaring 5 to 25, square root 25 back to 5. Now, if we're saying that the square root of some number a is b, that means that b times b equals a. So using the example we have up here, 5 times 5 is 25. So we would say the square root of 25 is 5 because 5 times 5 is 25. Now, there's a couple restrictions here so that we don't get outside of the real numbers, right? We could very quickly find ourselves in a location we're not super familiar with. So we first restrict b to be positive, which in other words, we're just saying that square roots can't produce negative numbers. Kind of like absolute values themselves are always positive, but we could always throw a negative sign in front of it and make it positive. But we'll put that on the back burner for right now. In general, square roots cannot produce negative numbers. So that's for square roots, but we're going to break that rule in just a tad bit. So if we're saying that the square root of a equals b, just check to make sure that b squared is a, that the b you're saying is the answer. Make sure that b squared equals a and that b is 0 or positive. So some rules we got to create here. The square root of x squared is what we would like to say is just x, but we got to be very careful here. It happens to be absolute value of x for all real numbers. So it's not just x, it's absolute value of x. Now, as time goes on, we're going to become a little lenient with this rule and just assume that all of our x's are positive, so we don't need to worry about absolute value. But technically, the very specific rule is absolute value of x. For example, the square root of -9 squared is not -9 because -9 squared is 81 and the square root of 81 is 9, right? 9 times 9, 81. Square root of 81 is 9. Notice that it was not -9. So square roots can only produce positive numbers. That's why we need this absolute value here. So please just be very careful about that. Similar rule, the square root of x whole thing squared is x for all non-negative numbers. So we want to restrict to make sure that these numbers are non-negative because square root of -5 whole thing squared isn't -5. And this is because square root of -5 doesn't exist to begin with, right? If this part can't exist, then when you square it, it still doesn't exist. Now, we're going to come back around to what we can do with this in a couple of sections in 1.4. But for now, we're just going to say this is, it doesn't exist. We can't do that. Okay. However, but square root of 6 squared, well, square root of 6 squared is square root of 6 times square root of 6 using what exponents mean. Square root of 6 times square root of 6 would be square root of 6 times 6. We don't really have a rule for this just yet. We'll see it in just a moment. But 6 times 6 is then 36, and the square root of 36 is 6. So we could have jumped from square root of 6 squared is just 6 because 6 is non-negative. Product rule, speaking of that, square root of 6 times square root of 6 is square root of 6 times 6. Product rule says we are allowed to split up multiplication and only multiplication so long as those a's and b's are both positive or 0. Likewise, we can split up division, we can split up quotients so long as the numerator is 0 or positive and that b is positive. So we want to make sure there's no 0 in the denominator. There we go. So as we've seen with a couple of things in this course, that we can split up multiplication, we can't split up addition or subtraction. So just to show you the inner workings of what really happens when we try to evaluate a square root, we are not going to evaluate these like this forever, but just to show you. So square root of 121, we're looking for the number that when you multiply it by itself, you get 121. Well, 121 is 11 squared. And when we're saying we have square root of something squared, that's this rule right here. Square root of something squared is the absolute value of that something, and the absolute value of 11 is 11. So the square root of 121 is 11. We don't need to do steps like this every single time, right? We kind of have an understanding of what square roots are on a surface level, so don't worry too much about that. For example, square root of 25 over 81. Well, division, we are able to split up and say square root of the top divided by square root of the bottom. Square root of 25, what number multiplied by itself gives us 25? 5. And what number multiplied by itself gives us 81? 9. So the square root of 25 over 81 is 5 over 9. Square root of 117. Well, square root of 117 itself isn't a perfect square, but what you're going to see a lot in this section is that we would like to simplify square root expressions or irrational exponent expressions. So what we can do is rewrite 117 so that at least one of its factors is a perfect square. Now, you might not know this right off the top of your head, but you could check factors of 117 to see what works. And it so happens that 117 is equal to 9 times 13. Well, now we have a product. We're allowed to split up products to say square root of 9 times square root of 13, and we know the square root of 9 is 3. So instead of square root of 117, 3 times the square root of 3 times the square root of 13 is a little bit more precise than square root of 117. There will come a time that we're okay with square root of 117 just in general, but as you know, as we're learning to manipulate and work with square roots, we like to write this instead. However, let's say that you didn't know that 117 is 9 times 13. Let's say you're just going along and checking factors of 117, right? You try dividing by 2 and dividing by 2 doesn't work. And then you try dividing by 3 and you see that 3 works. And you say that 117 is 3 times 39. Okay, well, we're not quite done yet because 39 is not a perfect square. However, we can rewrite 39 as 3 times 13, doing the same thing that we had before. Okay, well, you might notice that 3 times 3 is 9, and again, square root of 9 times square root of 13, 3 square root of 13. So even if you don't find the perfect square factor right away, that's fine. Check factors and see if you find factor pairs like this 3 and 3 to get that perfect square factor. Okay, some more examples. Square root of 6 times square root of 12. Well, this is a product. Why don't we combine it to square root of 6 times 12? 6 times 12 is 72. And what we're now looking for is a factor of 72 that is a perfect square. Well, you can think about it a little bit. What I'm thinking is that 72 is 36 times 2. Square root of 36 times 2 is the square root of 36 times the square root of 2. And we can say the square root of 36 is 6. What number multiplied by itself gives us 36? 6. Or what you could have also done is say that square root of 12, well, 12 is 6 times 12. Well, now we have square root of 6 times square root of 6 times square root of 2. Square root of 6 times square root of 6, square root of 36, and we get 6 square root of 2 that way. So a couple different options you have when it comes to simplifying. Another example, another division, square root of 36 divided by square root of 3. Well, division, we can recombine back into one square root. Square root of 36 over 3 would be square root of 12. Find a factor of 12 that is a perfect square. Well, 12 happens to be 4 times 3. Square root of 4 times square root of 3 would be 2 square root of 3, right? Square root of 4 is 2. Square root of 3 just stays square root of 3. Okay, but we're going to come back to this one. Maybe there's a different way of evaluating this one, maybe in 2 subsections. Another example, square root of 48x squared. So even though we have numbers and we have x's, that's okay. Fear not. Let's take care of the number and the variable separately. Find me a perfect square factor of 48. You can think about it. The answer would be 16 and 3. So we have square root of 16 times the square root of 3 and square root of x squared. Well, this is a rule that we have very specifically. Square root of x squared is absolute value of x. So again, square root of 16, 4, square root of 3, square root of 3, square root of x squared. It's on that very first line of examples, is absolute value of x. And just as a nice way of simplifying this or rewriting this more nicely, let's put that absolute value x in front. So in general, try not to write things to the right of the square root if it is not inside a square root. So notice here, square root of x squared became absolute value of x, not underneath a square root. If it doesn't have a square root, write it to the left so that you're not accidentally putting it over a square root. Okay. Well, we did 16 and 3, but 16 and 3 might not be your only option. What if we instead use 4 and 12? Well, if we split up 48 as 4 times 12, well, we could say that square root of 4 is 2, but square root of 12 is 4 times 3 again. Okay, so we have square root of 4 times square root of 4 times square root of 3 times square root of x squared. Well, square root of 4 is 2, square root of 4 is 2, square root of 3 does not change, square root of x squared, absolute value of x. Everything that is outside of the square root, combine them. Everything that is inside a square root, combine them. 2 times 2 is 4. 4 times absolute value of x is 4 absolute value of x. And what you could have also done is tried 6 and 8. So I will let you try that on your own. If you did not see 16 and 3, if you did not see 4 and 12, point is you can get to the same answer. It might just take you more steps. As we've been saying it, just because it takes more steps, just because you're a little inefficient, does not necessarily mean you are wrong. Okay, well, we just talked about our square roots, but square roots aren't the only type of root or radical that we can talk about. So let's talk about the general nth root. So square root says, take some number, multiply it by itself, it gets you some number. Cube root says, what if we do 3 of those numbers multiplied together? So this says the cube root of a equals b means that b times b times b is a, or that b cubed is a. Fourth root would be fourth root of a equals b means that b times b times b times b total of 4 times equals a, or b to the 4th equals a. Fifth root we write as fifth root of a equals b, and this would be b multiplied by itself 4 times, so b times b times b times b times b, a total of 5 times, equals a, or b to the 5th equals a. And we can go so on. So we've talked about square roots where it's just that number times itself, a total of 2 times, and now we can just do it as many times as we want. So this can continue infinitely. In general, if we write square root of x, there's an imaginary 2 here, right? It would kind of match and follow this pattern of b cubed equals a, b to the 4th equals a. But just in general, when it's a 2, we don't necessarily need to write the 2. So there's some nth root rules at play here. Because square roots, we know the inside has to be positive because we can't take square root of a negative number. But maybe that kind of bends when we allow our roots to be a little different and not just 2. Okay. If the inside is positive, if the inside to your root is positive, so if a is positive, then no matter what the root is, square root, cube root, 4th root, 5th root, so on, as long as the inside's positive, the answer, the expression will also be positive. Okay, so inside's positive, whole thing's positive, nothing weird going on. But the second we allow the inside to be negative, weird things can happen. So let's say the inside is negative and the root is odd. So we're talking cube root or we're talking 5th root. Well, if the inside is negative, but the root is odd, then the nth root of a will also be negative. So for example, what we're allowed to have is the cube root of negative 125. Not the square root of negative 125. Square root would be an even root. We're talking odd roots like 3 or 5. So we can evaluate cube root of negative 125. That answer is negative 5, since negative 5 times negative 5 times negative 5 is negative 125. So that satisfies the rule that the cube root of some number means this number cubed should equal the inside. So that's kind of weird, a little uncomfortable that we're allowed to have negatives sometimes and not other times, but the key here is whether or not the root is even or odd. So likewise, if the inside's negative but the root is even, then that whole expression is not a real number, right? So for example, square root of negative 4. Find me a number multiplied by itself that gives you negative 4. Well, you might be really inclined to say 2, but 2 times 2 is positive 4. You might be inclined to say negative 2, but negative 2 times negative 2 is positive 4. So we don't have a square root of negative 4 just yet. Like I said, we're going to come back to it in a couple sections, but for now, square root, fourth root, sixth root, if it's an even root and a negative number, they do not exist. So please be very careful of that. It is very important to note that if the inside's negative, it doesn't necessarily mean that it does not exist. It entirely depends on the root. Okay, if your inside equals 0, then the nth root of 0 is, you guessed it, 0. If n is odd, then the nth root of n is just that answer, a. Okay, well, think back to when we had square root of x squared. I told you that's the absolute value of x. But now we're saying if we have nth root of a to the n for any power, it's just a. However, the stipulation here is that this root needs to be odd. Well, if that root was then even, for example, square root of x squared, then we get absolute value of that inside. So please, this is really, really important here. The difference between having an even root and an odd root are completely different questions. They share some similarities, they share a same general property, but on the whole, some things are okay in odd roots and some things are not okay in even roots. So please just be very careful when you're evaluating these things. Okay, another weird example we might have is the mth root of the nth root of a. In this very weird scenario, we just say mth root, and nth root is the m times nth root. This doesn't happen a lot, but it is still an interesting enough property. Okay, so let's do some examples. Again, if the root is odd, then nth root of a to the n is just itself. But if the root is even, then the nth root of a to the n is the absolute value of a. Okay, so cube root of 27 would be 27 is 3 cubed. So cube root of 3 cubed, this root is odd, so the answer is just itself 3. Odd root, all we do is take whatever it is, no absolute values. Likewise, cube root of negative 64. Well, negative 64 is negative 4 cubed. So odd root, odd power, or matching odd power, I should say, the answer is just negative 4, because negative 4 times negative 4 times negative 4 is negative 64. Odd roots are okay to have negative numbers, and it's okay that they produce negative numbers. Okay, but likewise, fourth root of negative 3 to the fourth, well, this is now an even root with a matching even root. That would be this rule right here. So this would be absolute value of negative 3. Well, the absolute value of negative 3, going back to P1, is positive 3. Or similarly, if you don't really like or understand why this is, don't forget that negative 3 to the fourth -3 times -3 times -3 times -3 is positive 81. And now you see how we have to get a positive number when it comes to even roots. So what number multiplied by itself 3 times, total of 4 times, is 81? 3. So 2 ways you can do it. Even roots, you need to be careful. Odd roots, you don't need to be as careful because we are allowed to have negatives inside an odd root. Okay, some other weird examples. Cube root of 135. Well, 135 is not a perfect cube root like 64 or 8 or 27. However, we can split up 135 to have one factor that is a perfect cube root. Think about when we were doing square root of 72 earlier. We changed 72 to 36 times 2 because 36 is a perfect square root. Well, instead of perfect square root, we're just looking for a perfect cube root now. So it so happens that 135 is 27 times 5. So we can split up cube root of 27 times 5 as cube root of 27 times cube root of 5. Cube root of 27 is 3, and cube root of 5 is just cube root of 5. Nothing we can do there. Cube root of 18 divided by 64. Well, same thing. We can split up division as cube root of 18 divided by cube root of 64. Not anything we can do with 18, but cube root of 64 is 4. 4 times 4 times 4 is 64. Okay, fourth root of 162, x to the fourth. Let's start by handling the number and the variable separately. Look at this right here. Even root with a matching even power. So that's like the other rule that has absolute value. But for 162, we need to find a factor of it that is a perfect fourth root. Okay, 162 is 81 times 2. We know the fourth root of 81. What number times itself 3 times for a total of 4 times is 81? Well, 3 times 3 times 3 times 3 is 81. So we have 3 times the fourth root of 2. Nothing we can do with the fourth root of 2. And then fourth root of x to the fourth is absolute value of x. Again, even roots with matching even powers create absolute values. Odd roots with matching odd powers do not do this. Okay. And again, we like writing our absolute values are everything outside of a square root to the left of the square root. Okay, some other weird things we can do. We can also simplify expressions with differing square roots. So square root of 45 and square root of 20, they're not the same root. We can't simplify them. However, if we simplify the roots first, maybe we can simplify them after that. So 45 is 9 times 5, and 9 is special because that's a perfect square root. 20 is special because 20 is 4 times 5, and we like 4 because 4 is also a perfect square root. Square root of 9 is 3, so 3 times the square root of 5. 4, square root of 4 is 2, so 7 times 2 square root of 5. Well, 7 times 2 square root of 5 is 14 square root of 5. And now, just be very careful. Imagine that these square roots are x's. If this was 3x plus 14x, you would say it was 17x. Only difference is these are square roots. So 3 square root of 5 plus 14 square root of 5. You have 3 apples. I give you 14 apples. Now you have 17 apples. One more. Fourth root of cube root of 15. That's that one very specific, very fancy, weird-looking rule that says if we have a root of a root, we just multiply those roots. 4 times 3 is 12. So 12th root of 15, nothing we can do there. I just wanted to demonstrate how that one rule would work. Okay, some warnings before we move on to the next part. Some warnings of things you're not allowed to do. We've said that we can split up multiplication and division. We cannot split up addition and subtraction. So square root of a plus or minus b is not the square root of a plus or minus b. Big no-no. We can split up multiplication. We cannot split up addition, subtraction. That is true even for nth roots. Just because this is not square root and it's an nth root, still can't split it up. Okay, even if we have nth root of a to the n plus or minus b to the n, we can't magically cancel out those roots, right? We can only split up, we can only distribute over multiplication and division. If a doesn't equal b, so these insides are not equal, even if the roots are the same, if the insides aren't the same, we can't combine them. So here, the roots are the same, right? Nth root and nth root. Since the roots are not the same, we can't combine them. Likewise, let's say the insides are the same, but the roots aren't the same. We are not allowed to combine them via addition or subtraction, even if the insides are the same. The only time we can combine via addition or subtraction is when the roots are the same. So we have n and n. Roots are the same. That's good. A and A. Oh, the insides are the same. That's good too. So if the roots aren't the same, can't combine. If the insides aren't the same, can't combine. So roots are the same, insides are the same. I have one apple and I give you another apple. Now we have two of those apples. So be very careful when it comes to combining these things. Okay, well, that's talking about roots, and we want to really get into what rational exponents are to cap off chapter P. One more thing to do before we get to that is rationalization. So in general, somewhere along the way, it was decided that we don't like having square roots in the denominator. It's okay sometimes, but just we consider it mathematically sound to not have radicals in the denominator. So rationalization just says multiply the numerator and denominator by something that would cancel out the square root. So in the very basic case where the denominator is just a single square root, just square root of 2, all we're going to do is multiply by that exact same square root. So square root of 2 in the denominator, let's multiply by square root of 2 over square root of 2, right? Square root of 2 over square root of 2, oh, well, that's just 1. Multiply by 1, we don't change anything. Like I said, we're going to use that tool a lot over the course of this course. So square root of 2 over square root of 2, multiply the numerators across, multiply the denominators across, right? Just fraction multiplication. Square root of 5 times square root of 2, square root of 2 times square root of 2. Well, 5 times 2 is 10, 2 times 2 is 4, and the square root of 4 is 2. So all we did was multiply by square root of 2 over square root of 2, and what we get is something a little more sound, a little prettier to look at than square root of 5 over square root of 2. Again, we got rid of the square root in the denominator. That's typically what we like to do more. Well, we can get very complicated looking square roots, so that's not always going to be the answer. In some cases, we might have square root of something plus or minus square root of something else. So what we're going to introduce now is the phrase conjugate, and we're going to use this term a lot over the course of the entire study of college algebra, right? So the conjugate of A plus B, we say, is A minus B. So the conjugate is almost identical, except instead of A plus B, it's A minus B. Well, likewise, the conjugate of A minus B would then be A plus B. And what you're going to find a lot, and that's on purpose, is that conjugates come in pairs. So the conjugate of A plus B is A minus B, and the pair A plus B and A minus B is a conjugate pair. So the conjugate method for weird-looking square roots is to multiply by the conjugate. And what our goal is to get is if we multiply A plus B times A minus B, oh, this should look really familiar because this is A squared minus B squared. Okay, right? Don't forget difference of squares. A plus B, A minus B is A squared minus B squared. I told you we were going to talk about that a lot. So please don't forget this part. Okay. So let's say our denominator is square root of x. plus or minus square root of y, we want to multiply by the opposite sign, but still square root of x and square root of y. So if this is square root of x plus square root of y, multiply by square root of x minus square root of y. If this is square root of x minus square root of y, multiply by square root of x plus square root of y. Okay, and we do that because square root of x plus square root of y multiply by its conjugate, square root of x minus square root of y. And now what you should see, a plus b times a minus b. Oh, that's right here. A plus b, a minus b, a plus b, a minus b. So what this becomes is a squared minus b squared. So we're going to take square root of x, square it, minus, take y, or square root of y, square it. And we said square root of x squared is just x, square root of y squared is just y. And just like that, notice there are no more square roots. Okay. So let's just do one very brief example of that. 2 over square root of 7 minus square root of 5. So square root of 7 minus square root of 5, that's 2 square roots in the denominator. We don't like that. So let's multiply by the conjugate. Well, the square root of 7 minus square root of 5, its conjugate is square root of 7 plus square root of 5. So what we're going to do is multiply the numerator and denominator by square root of 7 plus square root of 5. Again, we can cancel this out and just make it 1. So we're not changing anything. Okay, well, let's multiply these things together. 2 times square root of 7 plus square root of 5. Square root of 7 minus square root of 5 times square root of 7 plus square root of 5. Oh, what you should notice is this is a minus b times a plus b. That is a squared minus b squared, right? Difference of squares, a minus b, a plus b. So what we can do is a squared minus b squared. Again, let me flash it on screen. We have a minus b times a plus b, same thing as what we have here. And what it simplifies to is a squared minus b squared. If you don't like what I'm doing here, that's fine. FOIL this out. Do square root of 7 times square root of 7, square root of 7 times square root of 5, square root of 5 times square root of 7, square root of 5 times square root of 5, and you'll see we get the exact same thing. Okay, well, this is really nice because square root of 7 squared is just 7. Square root of 5 squared is just 5. 7 minus 5 is 2, and we can cancel out those 2's. This step of canceling out this 2 and this 2, kind of just a nice cooked example so that, you know, the 2 could cancel out. But even if it doesn't cancel out, as long as there are no more square roots in the denominator, that's what we prefer. So let's go back to that example I said we would come back to. Square root of 36 over square root of 3. What we did for this one before is simplify it to 36 divided by 3, 12, and then did square root of 12. But let's see what happens when we just rationalize. Square root of 36 is 6. And to rationalize, we're going to multiply by square root of 3 over square root of 3. Okay, square root of 3 times square root of 3 is square root of 9. 6 times square root of 3 is just 6 square root of 3. Square root of 9 is 3, and 6 divided by 3 is 2. And that's the same answer we got before when we looked at this example for the first time. However, I want to stress, don't try and cancel things out that are inside a square root with things that are outside the square root. Notice that this is square root of 3 and square root of 3 and 3. Just because they are both 3's does not mean we can cancel them out, right? This 3 is stuck inside a square root. This 3 is not. We can only combine things that are outside square roots with things outside of the square root, and we can only combine things inside the square root with other things that are inside the square root. and that's rationalization. So very last part of this section are rational exponents, and we have finally built up to the point that we're able to do rational exponents. They're a little weird, a little funky, but what you're going to see is that they actually end up just changing the things we've already done. So in general, the nth root of a is a to the 1 over n. So there is a connection here. We've been doing roots this entire time, but what roots really are fraction exponents. So square root of a is a to the 1/2. Cube root of a is a to the 1/3. Fourth root of a is a to the 1/4. Fifth root of a is a to the 1/5, and so on. But if we want to know what the rules are for a to the 1 over n, well, they're just the same rules that we had for nth root of a. You know, inside is positive, whole thing is going to be positive. Inside is negative, and that root is odd, well, it's going to be negative. Inside is negative, and the root is even, not a real number. And if it's 0, same thing. So all this is just another way of looking at it. And what you're going to see is the first few examples are just very easy to change, but we're going to make all of those exponents look really weird when we try and go backwards. So for example, 16 to the 1/2, well, to the 1/2 is the same as the square root. So 16 to the 1/2 is the same as square root of 16. And we know what the square root of 16 is. So square root of 16 is 4. Okay. Negative 27 to the 1/3. Well, negative 27 to the 1/3. To the 1/3 means cube root. Cube root of negative 27, negative 3. And we should be pros at that by now after doing it a whole bunch of times earlier in the section. 1 over 16 to the 1/4. Well, division, just like all the rules we've had before, 1 over 16 to the 1/4 would be fourth root of 1 over 16. We can do fourth root of 1 divided by fourth root of 16. What number multiplied by itself 3 times gives you 1? Well, that's 1. What number multiplied by itself 3 times gives you 16? Well, 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. 32 to the negative 1/5. Well, just like rules we had in previous sections, negative exponents, we drop them to the denominator. 32 to the 1/5 means fifth root of 32. What number multiplied by itself 4 times for a total of 5 times gives you 32? Well, 2 times 2 times 2 times 2 times 2 is 32. So fifth root of 32 is 2. Negative 5 to the 1/4. To the 1/4 power means fourth root of negative 5. And we can't take even roots of negative numbers. We can take odd roots of negative numbers. We cannot take even roots of negative numbers. So negative 5 to the 1/4, fourth root of negative 5 does not exist. However, all of these exponents have all been 1 in the numerator, 1 in the numerator, 1, 1, 1. Is that the only thing we can do? Of course not. So what if we want to go backwards? What if we're given an expression that has a rational exponent and we want to use roots to be able to evaluate these things without a calculator? So the rules of integer exponents can be extended to rational exponents. All the rules that we had for integer exponents, like the product rule, quotient rule, power of a power, all of those rules still true for rational exponents. So what we can do is rewrite something like a to the m over n, right? Before, all the examples we had before was like 1 over 2, 1 over 3, 1 over 4, and so on. So what if instead that numerator is anything and that denominator is anything? Well, what we can do is 2 things. First thing we can do is say that m over n is m times 1 over n. That's true, just going backwards from fraction multiplication. But now a to the m times 1 over n, we can again go backwards and use power of a power. Oh, right? This is what we did, I think, in P2, right? P2's exponents, I'm pretty sure. Well, if I gave you something like this back then, you would have said, oh, power raised to a power, we multiply. Oh, so we're just going backwards now. So a to the m over n is a to the m to the 1 over n. However, 1 over n power is the nth root. So a to the m over n is the nth root of a to the m. But that's not our only option. Think about multiplication. This is not the only order we could have done this. We could have also done a to the 1 over n times m, just multiplying backwards, right? 2 times 3 is the same as 3 times 2. So 1 over n times n, a to the 1 over n times m. Well, this is a to the 1 over n to the m, and this says nth root of a raised to the mth power. So we have two options for how we can split the exact same thing. And what you're going to see in all the next few examples is that there isn't really a perfect science as to when you want to use one of these decompositions versus the other. Sometimes it just comes down to how big and small your numbers are. Sometimes if you have really small numbers, maybe using one is better than the other. Or if you have really big numbers, maybe using one over the other is easier. So let's do a couple examples of this. 8 to the 2 over 3. Well, our first way says to split up 8 to the 2/3 as 2 times 1/3. Okay, well, 8 squared is 64, and 1/3 power means cube root. So 8 squared is 64, and 1/3 power means cube root. What's the cube root of 64? 4. 4 times 4 times 4 is 64. Okay, that's one option. But what if we did it the other way? 8 to the 2/3 can also be 8 to the 1/3 squared. So this says do cube root of 8 first. What's the cube root of 8? What number multiplied by itself twice gives you 8? 2 times 2 times 2 is 8, and 2 squared is 4. Same answer. The answer to the whole thing is 4, but maybe you prefer one of these two ways over the other. Sometimes one of these ways is way too difficult. Sometimes the other of these two ways is way too difficult. So whichever one happens to work, and if you happen to use one way and it's inefficient, but you got the right answer, you don't need to do it the other way. Either you get the right answer or you don't. Okay, negative 16 to the 5 over 2. Again, we've talked time and time again about the usage of parentheses. There's no parentheses here. So this is saying just 16 to the 5/2. So again, option 1 says to do the numerator power first, 16 to the 5th, and then to the 1/2. Well, 16 to the 5th is, yeah, there you go, 1,048,576. And then 1/2 power says square root of that number. And I don't think many of you happen to know what the square root of this number is. It is, of course, 1024. But maybe not super obvious. Well, what if we went the other way instead? What if we instead did the to the 1/2 power first and then raise it to the 5th power? Well, 16 to the 1/2 says square root of 16. Square root of 16 is 4. And 4 to the 5th is 4, 16, 64, 256, 1024. So negative 1024. Well, both of these ways dealt with really big numbers. There's no way we could get away from not having a really big number, but at least one of the ways the numbers weren't so daunting right away. So how to know which one is going to be which? It entirely depends on the question. Okay, 100 to the negative 3/2. Well, again, from P2, What do we do with negative exponents? We drop them to the denominator. Okay, first way says do 100 cubed and then do to the 1/2 power. 100 cubed is 1 million. 1 million to the 1/2 says square root of 1 million. And square root of 1 million would be 1,000. Okay. All right. Well, let's go the other way. Let's do square root first and then raise it to the 3rd power. What's the square root of 100? What number times itself gives you 100? That would be 10. And 10 cubed. Oh, okay. That's a little bit nicer to deal with. Okay, and now that we've done a couple examples of what these rational exponents mean, let's just do one final frontier of examples to cap out chapter 6, doing all sorts of weird exponent stuff. And like I said, the rules of rational exponents are the exact same as rules of integer exponents. So for example here, 2x to the 1/3 times 5x to the 1/4. Well, if this was 2x cubed times 5x to the 4th, you would know exactly what to do with this. You would do 2 times 5 and x cubed times x to the 4th. Only difference is that we now have rational exponents. All the exact same steps. Only thing is we now need to use rules of fractions to be able to simplify x to the 1/3 times x to the 1/4. Stuff like this, you might be asking, do you need to change it back to a root with a radical? You do not. In some cases, if you get like 1/12, where 1/12 is very clearly the 12th root, you could. I will not hold that to you, but in other courses, they might hold you to it. But for example, x to the 7/12, it's not going to look any better with a radical involved. 21x to the negative 2/3 over 7x to the 1/5. Okay, well, we combine the numbers and we combine the x's. Well, 21 divided by 7 is 3. X raised to some power divided by x raised to another power. Well, when we were dividing, we subtracted. And same thing, just because those exponents are now fractions, it doesn't change anything. It just makes our combination a little bit more difficult. So speaking of things we do and don't simplify, negative exponents are one of those things that we should always simplify. X to the 3/5 to the negative 1/6. This is x raised to some power, raised to another power. What do we do in power to a power? We multiply. Well, fraction multiplication just says multiply the fractions divided by, multiply the numerators divided by multiply the denominators. 3/30 is 1/10. Negative exponent drops to the denominator. And this is an example of something that wouldn't be so bad to change to 10th root of x. Now you might be saying, well, this is a square root in the denominator. We should be rationalizing that. It kind of, this is not a square root, this is a 10th root. So for us to rationalize a 10th root requires a little bit more work than just plain square roots. I don't think I will ever ask you to rationalize something that is not a square root. Everything there is a square root, but you could rationalize it. It's just a little bit more work when it's not square root. 10th root, a little bit more work. 8th root of x squared. Well, 8th root says to the 1/8. Well, now we have a power raised to a power, so we multiply those powers. 2/8 is 1/4. And x to the 1/4 is 4th root of x. Oh, that's kind of weird looking. These things happen. Okay. Well, square root of cube root of x to the 8th. Well, you could use that rule we were talking about earlier with root of a root, but let's go a slightly different way to simplify. Well, on the inside, x to the 8th, cube root of that says x to the 8th to the 1/3, right? Cube root of x to the 8th says x to the 8th to the 1/3. Well, power raised to a power, we multiply. And now square root of x to the 8/3 says x to the 8/3 to the 1/2. power to a power, we multiply, fraction multiplication, and simplifying a fraction, x to the 4/3. Who would have thought that this right here would simplify to a nice, pretty x to the 4/3? One more. I don't know if it's actually the one more example, but we'll keep going, right? 16y to the negative 2 over x to the negative 8/3 raised to the negative 1/4. Well, everything on the inside multiplied or divided together. Let's distribute that negative 1/4 power to everything. Here, fraction multiplication, fraction multiplication. Let's simplify those fractions. And also 16 to the negative 1/4, negative exponent drops down to the denominator. 16 to the 1/4 says 4th root of 16. 4th root of 16 is 2. Y to the 2/4, y to the 1/2, x to the 8/12, x to the 2/3. Well, I wouldn't really change x to the 2/3, but y to the 1/2 we know is square root of y. Okay, and that was the last example. So that is the end of chapter P. There's a lot of information in chapter P. I seem to think or have found that in future chapters, so if you're watching into chapter 1, chapter 1 is about solving equations. So I think some people prefer solving equations over just dealing with kind of abstract expressions, kind of just out in space, so to speak. So there's a lot of information, a lot of basic rules, stuff like that. But fear not, chapter 1, we're going to use a lot of these rules, but when we're solving equations, it seems a little bit more purposeful. So with that said, thank you so much for watching for chapter P, and I will see you in chapter 1. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.